Hi, hello everyone. I'm Chris Phillips, and I'm welcoming you to our course on machine learning for neuroimaging. Learn the basics before going deeper. So this was also co-organized with Janaina, Mourao-Miranda. She's not around at the moment. So just a brief introduction for you guys. So just a reminder, the goal today is really to go through the basics of machine learning. So the course is planned and organized for beginners. And the key issues are really to make sure that you know how to process your data and be rigorous when it comes to the methods. They are the do's and don'ts of the techniques, their limitations, and also importantly, how to interpret the results that you will obtain. And that, of course, will depend on the questions that you are asking. We'll illustrate that with different modalities such as functional and structural MRI, but there'll be also applications in cognitive and clinical neuroscience. So the program or the menu for the course includes 10 lectures. The 5 here on the left, they are mainly for introductory topics. I'll be talking afterwards about what is really the machine learning, what are the concepts, and then the rest will be about making inference, accounting for confounds, how to test things in the framework of machine learning. The other 5 lectures are probably a bit more advanced and will tackle more specific issues with functional MRI, unsupervised learning, deep learning issues, and clinical applications. And Thomas will conclude the day by contrasting the different approaches. And with that, I hope that by the end of the day, you'll be able to master the tools that you have mentioned. And as the code wisdom goes, the important thing is to know when you shouldn't be using those tools. Thank you. Hi, it's me again, Chris Phillips. So I'm now starting the course with the introductory presentation and orient you about what we really are talking about when it comes to machine learning. So the outline will be really about introductions of the main concepts associated with pattern recognition and machine learning, especially in the field of neuroimaging. There'll be issues about the different types of models. I will tackle some concepts about regularizations, kernel methods, and importantly also about how to make inferences and validate the tests that you are doing. So first of all, pattern recognition is really about finding regularities in the data that you have. That's not a new concept. And actually, this is something that is used every day by the industry. And different applications and very common applications are these ones where the mail post will be recognizing digits written on your letters. You certainly heard of face recognition techniques that lets you recognize different people in the pictures that you have on your computer or by cameras placed on the street. And for more fun applications, you have Amazon and Netflix that can do very good recommendations based on your profile. There are different types of learnings or machine learning techniques. And the main categories are supervised, unsupervised, and reinforcement. Here, I will mainly focus on the supervised approaches. That is when we train the machine, the computer, with a full data set where we have labeled data. So we know the data and we know the associated labels. There are other techniques that do not include the labels for the data, so they are unlabeled data, and these these are more closer to things that we call clustering. So we try to associate data together. Valeria, in one of the lectures, will address that topic. The last one is not really used in machine learning. It's called reinforcement learning. That has more to do with robotics, where the aim is to maximize some cumulative reward over time. So it's really about taking actions when events occur. So it's not directly related to our field for today. So the first and the classical example for classification is when you can split your data into two classes. So these are discrete samples in class 1 and class 2. They are, for example, patients and controls, and you want to learn to differentiate them. So there is to be some training that will output a predictive function. And with that predictive functions, when given a new subject, you'll be able to predict the class membership. And in this case, because you've trained it on patients and controls, it will spit out a value that will either refer to patient or the control class. The other typical application is a regression model. That is when the label, the target that we are going to try and estimate, is a continuous value, so it's not discrete. And here, for example, that could be any type of scores over some scale. Similarly to the classification, you can train the machine based on the data, on the images and the target values. And then you will have, for a new subject, the possibility to predict the score that new subject would have obtained based on what you've learned from your training set. So these are the two main families of machines that I will be talking about today. With respect to mass univariate, in comparison to multivariate approaches or pattern recognition, I want to highlight something that is critical, and I will come up many times in my lecture, but also that of my colleagues, is that with mass univariate, with the standard GLM SPM analysis, we start with some data on which we apply a model, and then we can make some statistical tests, and we correct for multiple comparisons in order to get a statistical parametric map. So here we know in advance, pretty much we want to figure out where in the data, where here the blue and orange blocks, where does the model fits the data. With pattern recognition, things are a bit different and actually working the other way around. We start with the data, and they can be from task 1 and task 2, so that's like the label in class 1 and class 2. And then you want to figure out how to separate those, and that will give us some predictive map. Then for a new example, we can predict the label associated with those data. So it's actually working in the other way around. And the key issue, or the key point here, is really that we are working about doing prediction on out of sample, while for the standard approach, all the data are used at the same time to fit the model. And of course, because these are completely different processes, the maps that we obtain at the end have a very different meaning. Here, this is about making an inference about voxel being associated or no with the task the subject performed or the classification of the subject. Here, it's not about associating a single voxel, it's the whole pattern that is meaningful. And we can't do any inference on those. I'll come back to that later on. So the advantages of pattern recognition, very broadly, we can expect that a multivariate analysis will be a bit more sensitive because we are using the whole pattern in the image to make our inference. And the inference is again about the target, either the label or the associated score. And the second advantage is, of course, that this is a predictive framework. So we can predict for new samples what should be the associated target value. It comes with two drawbacks. And the first one is obvious, I've just mentioned it. We don't do local inferences about which bit of the brain is involved if you're using the whole brain. And typically, in order to get good prediction, we need a lot of data. More, actually, than would be sufficient to get statistically significant results with the standard univariate approaches. So what are we talking about? The whole brain, so take a brain image, it's only a bunch of voxels. And so for us, in machine learning, a sample will consist of a feature of feature vector, that is the values from all the voxels that we are interested in, and they'll be sort of stacked together. So the data dimensionality is the number of voxels. There are other types of features, of course. You can either look at the whole brain, or you can look at the subset part of the brain, a region of interest. You can include connectivity measures, cortical thickness, or whatever you fancy. The point is that the data associated with one sample, one individual, for example, will be represented as a single feature vector. So my classification model, to give you an example, a very simple example where I have two features per brain image. So I extract only two values from each image, from each subject. I can plot that in this 2D plot, and I can do that for all the images from class 1 and class 2 here in the pinkish and the bluish points. Of course, if you were using the whole brain, this would be a space as large as the number of voxels that you are considering, which I cannot represent here on screen. The idea of training is about finding a line, a hyperplane, that would be separating the two groups of data that you have specified. There are many ways of defining such a border, such a line between the two, but the key idea is that whenever you have defined such border, then when you have a new subject, a new image, you can place it in the same space and associate it with either one class of images or the other class of images. And in this case, this is obviously one image that would be coming from the second class. When it comes to regression, we're doing pretty much the same. So with a simplified example of extracting just two features per image, you can represent each image with their associated score. And you will, by training, you will find the line or the plane in multi-dimension that is fitting all the data I have. And similarly, whenever we introduce a new sample, we can guess what we can predict, rather, what should be the actual score for that subject. So here, what I've shown you are linear predictive models. So we are here defining a classifier or regression simply by drawing a line or a plane in the feature space. This is because in neuroimaging, the data are sufficiently large. Explain you what by that I mean, that we have lots of usually features, and therefore we'll be able to represent the whole model by a weight vector and a bias term. The idea is simply that for each sample, you can associate a value that you can calculate, and that value will depend on the weight vector and the bias term that you're using. And in this linear case, we can, for example, express this weight vector as a linear combination of my samples. So if I have lots of training samples, then I have more freedom to find an optimal W here. So my training is really about finding these W and B values. And in this case, it boils down to finding B and alpha I, i.e. the linear combination of my samples. This is my linear predictive model, and with the moment I know my W, that simply means that I have one value associated for each feature of my sample, so features being vector X. And if we're talking about a brain image, that means that for each vector, each voxel in my image, there is a corresponding weight in this W. And those weight can actually be represented as an image themselves, because that's just mapping from image to feature vector and vice versa. The key thing is this will be highlighting the relative contribution of each feature on my decision. So this shows here that these bits of the brain are contributing a lot to the decision taken. So it's informing us about the category. As far as I remember, that's an example where we are categorizing fMRI maps from people watching faces or objects. And this is the face, actually, this would be the face visit for Maria that would be involved in differentiating those two categories. But as I mentioned, we still cannot make local inferences. So the whole map has to be accounted and considered all together. Indeed, all these greenish voxels have a small contribution, but there are zillions of them. So put all the together, they could actually have as much importance as the red blobs here and the blue blobs over there. So we cannot threshold those maps and make inferences about the localization of the contributing parts of the brain. I know it's very tempting, but you simply cannot. Because, we move on to this common issue with neuroimaging, as I mentioned. Typically in a brain image, you have 100,000 voxels, but we rarely have a data set with 100,000 subjects. So we end up with a problem where there are more features than samples, more voxels than example subjects in the data set. And this leads to what mathematically expressed as a nil condition problem. So there is no unique solution to that problem. Possibilities to come out of this is to decrease the number of features. That is, we would just use smaller number of voxels. So that would be focusing on regions of interest. You can try some feature selection strategies, though it can be dangerous in terms of double dipping. So when you would be overtraining your model, or you can apply searchlight approaches, so where you focus on subsets of voxels in the brain. The other axis to solve that problem is to use regularization and kernel methods. So I will not focus on these because they are difficult. They have their own interest, but it's more important to focus on these ones, especially also if you use a small region in the brain, you easily end up with 4,000 or 5,000 voxels. And again, we don't have data sets with 50,000 subjects. So what do we mean by regularization? The aim is simply to find a unique solution and avoid overfitting. So we want to be able to generalize and do good predictions. And this typically involves finding a balance between fitting the data and a penalty term. And this penalty term tells us simply how these weights associated to each voxel should be distributed. The key thing is that different choices of these data fit and penalty terms will lead to different solutions. And I'm illustrating this with this example. So here we have a square loss. So we just want to use the loss in terms of getting the number of errors, if you want. And then depending on how you constrain the distribution of the weight, you will get vastly different weight maps. But crucially, all of these models have very similar errors. So they actually give you the same precision in prediction, but by using very different sets or width over of the voxels of the features in your image. And this is kind of disturbing because you could say that all those models are equally good, despite the fact that they involve the voxels in your image in a very different way. So the key thing is really to know what the machine that you're using, what sort of constraint here listed, variation, Laplacian, and so on, and in order to make sense of the maps that you will be obtaining, because they can be very smooth or very sparse. Another way of dealing with the dimensionality that is extremely useful is the kernel methods. And that's a whole family of methods that rely on that trick. And it allows us to do some classification and regressions. It relies typically on two parts, the kernel function and the mathematical algorithm to make use of that kernel. A kernel is a very nice way to summarize the content of your data. As you can see, it depends on two samples, so that can be the image of subject I and image of subject J. And for each pair of images, it will give us one number, Jij. In the case of a linear kernel, which we'll be using in NeuroImaging, we'll simply use a dot product. So it will be simply the scalar product of the vectors. So again, with a simple example of images counting only two voxels, two features, I can estimate the kernel value. What you will notice is that this kernel matrix has the dimension depending on the number of subjects. And as I mentioned in our problems, we typically have fewer subjects than voxels. The advantages of that formalism is that it's a general approach for regularization. So we take the whole image together and we condense each pair of images by a single number. It's also very efficient in terms of computation. And altogether, it can be linear, non-linear for this kernel formula, this kernel trick, but it's kind of measuring the similarity between the samples that you have. So I will just illustrate this. How does that fit in? Well, simply with this function, as I said, for prediction, we were using these weight vectors. And I said, yeah, the weight vectors can be constructed as a linear combination of my samples. In that case, replacing W by its formula, I can roll back to expressing the prediction for any subject based on this kernel function. So now I can work in terms of samples, and it will be possible to train and find these alpha I and B by working only with the kernel. And the example of kernel methods are the one that most people know about is support vector machines. But there is a whole zoo of other machines that exist, kernel-rich regressions, Gaussian process, kernel Fisher, and so on. The advantage of using a kernel is you can play with those kernels in clever ways. And I just want to highlight one possibility that we have is to combine kernels. So you can be combining multiple kernels. So you define something that is associated with subject I and subject J as the sum of two subkernels. And those two will sum up. And there are some constraints on the way you combine the kernels. That has to be learned on the way, so it's just increasing a bit of complexity. But you can see, for example, that with this, you could be combining data from different modalities or from different bits of the brain. You could use the left brain or the left hemisphere or the right hemisphere, and for each hemisphere, for example, calculate the kernel and then figure out which hemisphere is dominant for your prediction based on those kernel weights. And just to illustrate those kernel methods, I will explain you what is meant by the support vector machine. And as I said, it relies on a kernel representation, and it's called a maximum margin classifier. Well, assuming that we work again with a very simple problem where for each image only have two features, I have here represented data from 8 subjects in class 1 and 6 subjects in class 2. My goal is, of course, to draw a line, the border between those two classes, in order to make a prediction of. There are, of course, as I mentioned, many ways of drawing such a border between the two classes. And the idea behind support vector is to find the one with the largest margin. The margin being the distance between these dotted lines that go through the closest samples between the two classes. So I want to make sure that this margin, let's say the no man's land between the two classes, is as large as possible. This again simply means that I have to find this border that I can represent with a vector W and a scalar B. And whenever I'm calculating the value associated with some point, on one side of the border, I will get a negative value. On the other side, I'll get a positive value, and that will give me a prediction. A prediction that is, oh, sorry, I forgot to mention, this border is supported by only a few dots. And these are my support vectors, hence the name support vector machines. The alphas associated with those support vectors will have values different from 0. And support vector machine attracted lots of attention because it's a very fast and resilient machine. It gives us, in many cases, very good results. Unfortunately, this will only give us a hard binary prediction. And by that, I mean that you will be either on one side, so it will be you are either in the pinkish group or the bluish group, but it will not give you any intuition about how close you could be from the border, how close you could be from the other category. But people seem to like it, and it's still a very valuable method, and it's probably one of the easiest to work with to begin. Now, how do we know that our machines, after training, are doing a good job? And that's the key things. Remember that the quality of a machine is about being able to predict correctly the label associated with a new sample. This means that we have to check the out-of-sample predictions. And to do that, there aren't thousands of ways. We'll have to split the data set we have in two parts. There'll be typically a training set and a test set. And with a training set, we'll be able to train here, for example, a classifier. So we use all the data we have, the features, and the label +1 or -1. Once this training is done, we can then use the test images and the train classifier to predict the targets, the labels. And you get some output for these few test images. And now the key thing is we want to compare the true target, so the things that we know from the beginning, with the predicted target. And for example, here you will have like a mismatch, so that would be one error. And that's the key idea. We'll need to be able to split the data. And Pradeep, in I think the next lecture, will address these questions of validation and out-of-sample prediction. Because with small data sets, the way you split the training and the test will have to be rotated. So you will be resplitting your data multiple times in order to have an estimation of the validity of your predictions. Which actually, how do we measure that? And that depends, of course, on the type of problem problem that we are dealing with. And for classification, we'll typically speak of a confusion matrix that I have presented here. So you have here in this binary case, two classes, 0 and 1, and you can predict your image in one class or the other. Of course, if you have enough test data, then you can have an estimate of the number of times you right, that's the A and D, and wrong, that's the C and B over here. It can be false positive, false negatives, true positives, and true negatives. And with that, you can define your accuracies. There are different ways of defining your accuracies. That can be through total accuracy or class-specific accuracies, balanced accuracies. That depends on the type of problems that you have. There is, of course, also the notions of sensitivity, specificity, and predictive values. For regression, you would rather focus on the ability to find the true value, the predicted value, the target, the link between the target and the predicted. If your prediction was accurate, all the blue dots here would be on this red line. They are not, so we'll be measuring the distance from the truth. And that's simply estimated through this kind of formula where we look at the difference between actual, the true value and the predicted value, square that, sum it, and average across all your samples. Finally, how do we know that, for example, my accuracy is above chance level? Am I doing better than tossing a coin? And that calls for model inference. This will be addressed by the talks by Joram and Emanuele afterwards. But I'll give you just a primer on that. So the idea is, if you start with the null hypothesis that there are no link between features and target, and your test statistic is accuracy, then if there is actually no information in your data, in your features, then the labels could be just randomly permuted, and that wouldn't be affecting your accuracy. So you can estimate this distribution of accuracy under the null hypothesis of null relations, and then we'll be able to calculate a p-value. That is, what was the chance of observing an accuracy A under the null hypothesis of null relationships between my data and the target. Of course, permutations require some constraints on your data. It should be possible and doesn't work all the time, and that will be addressed by Joram. So all in all, let me conclude. If I draw a bridge between the univariate and multivariate approaches that I've shown you, well, whenever we speak of a voxel, the data element that we have in univariate is a voxel. Here we speak of a volume. The whole image is our sample of interest. In univariate, as I said, we specify the model. We know the GLM, for example, and we see how it fits the data. Here we try to infer the target from the data, so it's working in the other way around. In univariate stats, typically you will be looking at differences or correlations, while here you can see that multivariate, when you try to predict the class associated with a label, it's looking at the similarity or score for that subject. So is it a control or patient? So is my new subject closer to my controls or closer to my patients? Univariate typically will use a GLM. Here, I've mentioned the SVM and listed a few other machines. So there are different ways of fitting, of finding these relationships. GLM inversion is a linear problem. Machine learning training is a nonlinear approach, and that will require iterative methods. Some are fast, like for SVM. For other machines, it can be much slower, depending on the complexity of the machine and the number of parameters that need to be estimated. In univariate, we do inferences on a contrast of interest. Here, we are interested in the prediction accuracy with the cross-validation approach. training and the test set. And finally, with univariate, we make an inference about a voxel or cluster activation, so we know which part of the brain is active. And as I mentioned earlier, there is no way of doing that here. And with that, thank you for your attention. And I want you to be very careful when using those tools, because they can give you very nice results, but they may not be exactly what you wanted. Here are some references, and thank you again for your attention.
Hello, everyone. Thank you for coming. Today, I would like to walk you through this wonderful technique called cross-validation, which helps us properly assess predictive performance of different machine learning models and other statistical learning models. This video will be posted later, so you can go back to the video and pause and look at the slides, and then we'll also share the slides later, so you don't have to worry taking notes or whatnot. All right, let's jump in. The goals for today's talk are the following. The most important being to learn what is cross-validation and how to do it correctly, because it's complicated depending on your goals and how you implement it, and what are the effects of different cross-validation scheme choices depending on which one you pick, right? So some might be too conservative, some might be too lenient in terms of their bias towards evaluating performance, right? Simple, 3 goals. So to understand what cross-validation is, we need to understand what generalizability is. And generalizability is simply this, right? So let's say you have a data set called the sample, typically, as a statistical definition. As you can see it in a 2-dimensional space here, 2 groups, red and blue. And what generalizability is, if you fit a model to this sample, available data, and to make it even more concrete, let's assume it comes from the western part of the United States. And you want to, generalizability is basically the property of the model learning from a limited sample and being able to accurately make predictions on unseen data. That's called the population, which also has a statistical definition, right? So you learn from the limited sample, but you want to generalize to the entire population. This is really important to keep that in mind, because this point is often missed, and this is often also called out of sample prediction. And the basic rationale behind employing such technique is to avoid overfitting to the limited sample size, because the little sample we have on the left may not fully represent the entire population. So you don't want to overfit to that little sample, small sample. You want to learn the characteristics that are fully representative of the full population, right? This is keep in mind. It's not enough to learn the group differences between the 2 groups on the left here in the Western US. You want to learn the properties that generalize across the entire population. So a CV is a technique that helps us quantify generalizability, right? The way it is typically done is when you have a limited sample, such as the Western United States I showed you. Just to make it even easier, we can go by the existing geographical boundaries. Typically, what is done is to keep a certain section of the sample aside for evaluation and testing, and use the remaining for training, right? So like in this case, it's California here. And once you learn on the training set, evaluate in the test set, and you get some estimates of performance, and you repeat the process with different slices of the sample, right? This time Montana, right? And then you repeat it many times until you have a good estimates of performance as you shuffle through the data for different splits of training and testing. So the basic mechanic is that, right? It's quite simple. And the hope is that the estimates you obtained on these different splits of test reporting sets represent its performance on the entire population. That's the assumption, right? Because that's all we have when we are using to try extrapolate the performance of the entire population, right? That's the So why must we cross validate, right? So the reason is again pretty simple because we have a limited sample size, right? So when you use a very big training set, for example, bigger, if you try to make the training set bigger, you get better learning, model fits better to the training set. But when you try to make the test set bigger, you can have better evaluation of the model to see where it performs, where it doesn't perform, what are its quirks, etc. Right? However, however, these two sets must be disjoint because otherwise you are actually cheating, so to say, right? And because our data set, our sample size is fixed and often actually quite small compared to the properties that we're trying to measure, it's a bit of a tug of war in the sense that these two grow at the expense of each other, right? So, and cross validation is a technique that helps us to maximize both, right? Because you split, you randomize, take two random splits, try and evaluate, randomize again, try and evaluate, right? That way you will have uh, done the best in both in terms of fitting the best models as well as thoroughly evaluating their performance on new and unseen um, test sets, right? So that's the basic reasoning behind the cross validation. So what are the typical use cases of cross validation? They are essentially you use cross validation whenever you cannot set aside data for parameter estimation or validation of results, etc. Right? For example, to estimate generalizability, as we just discussed, test accuracy or reporting accuracy, we will call, and to pick optimal parameter. When you have multiple parameters, you want to pick the optimal one, and cross validation is a technique to help you do that. And third is to compare performance across different models after tuning your hyperparameters, right? So these are the typical use cases. There are a few others too, but these are the most predominant ones. So there are two key aspects of cross-validation. One is, as we mentioned, how you split the data set into training and test and reporting. And basically, you want to try maximize the independence between the training and test set because otherwise it's not a real test, right? If there is an overlap between training and test sets. Usually these splits are across samples, so called rows in the feature matrix, or sometimes, for example, classes could be healthy or disease. They could also be across time, for example, in the fMRI sessions, for task duration, right? Like cats versus chips, right? And two, how often you repeat these randomized splits, because that determines the thoroughness of the test you perform, right? You don't want the result to be an artifact of a random fluke, easy or hard split. You want a good representative, stable estimate of performance, which is why you want to repeat it as many times as possible. Right? Two key aspects. Simple. So in order to get the mechanics right in a practical scenario, for example, I'll just give you a schematic of the full setup required for cross validations here. So, for example, when you have a training set, you know that we use it to estimate the goodness of fit of the model, which means that this model is biased towards the particular training set it was just fit on, right? So you use a tuning set, a separate one, a tuning set, to optimize the parameters, pick the optimal parameters, right? And because you pick the parameters based on this tuning set, the optimal model is biased towards this particular tuning set. And in order to evaluate this optimized model, you need a separate third set and I call it the reporting set, right? Which is what you want to publish, put into your figures and tables in papers and whatnot, right? So this does evaluate generalization of the fully optimized model based on the training and tuning sets, because it's independent of the training and tuning sets, right? So you can imagine, because we have a limited sample, which is the whole data set, you can think of implementing the randomization and repetition of the cross validation this way, right? Take the whole data set, slice it into one training section, which consists of both training and tuning sets, and run an inner cross validation loop to really fully optimize the model for both its core and hyperparameters, and then evaluate that optimized model on the reporting set using an outer loop as you shuffle all these sets, right? So to really do the best optimization as well as the best evaluation of performance, you want to have these three sets: training, tuning, and reporting sets. Okay? This schematic is really helpful when you want to implement your own thing for your research. Just to clarify, of the just to have a better understanding of these three sets, and also because there is some confusion depending on the domain you come from, I made this little table. So essentially, the purpose of these sets, right? As you mentioned, the training set is used to train the model to learn its core parameters. The tuning is to optimize hyperparameters or meta parameters. The reporting set is used to evaluate the fully optimized model to report performance in papers and other competitions, etc. Right? What you do not want to do with these two sets is you don't want to report the training error as the test error. You don't want to do feature selection or anything supervised on the tuning set. It's a typo, it needs to be tuning set to learn and optimize. And you definitely don't want to use the reporting set in any way to train or optimize parameters, because that will compromise the whole exercise. So as I said, depending on the domain, tuning set is sometimes referred to as validation or test set, depending on if you're coming from computer vision or biostats uh, domains. The reporting set is sometimes referred to as test or validation. So these are switched. So I'm going to do away with these confusing terminology and introduce these three new names: training, tuning, reporting. No confusion there, right? No ambiguity. I strongly recommend you follow this as you go forward, right? So test set in the discourse online are different papers and the older literature, typically in like colloquial exchanges. Test set is often used as a loose term to refer to a split different from the training set, right? Don't take it too literally in an informal discourse. And training set is also often absorbs both the training and tuning sets, right? So you wanna like if you wanna exactly understand what's going on, always like double check with who you're speaking to or paper you're reading, right? So just keep that in mind. But I strongly encourage training, tuning, and reporting sets, right? Right. So to give you a concrete example of a cross-validation setup, one of the popular forms is called K-fold cross-validation. Imagine a sample of a data set of n samples, as I show here with blue circles. This works by basically splitting the data set into K folds or K bags or bins or whatever you want to call them, right? The purple, red, green, and cyan here, right? So one of these folds acts as the reporting set or tuning set, depending on whether it's inner or outer cross-validation loop. Let's go with the reporting now. Is acts as the reporting set. The rest is used for training and tuning. And as you repeat the process, each trial of this k-fold CV, one of the different folds access the reporting set, right? And you repeat it k times until all folds access the reporting set. And this way, you have the reporting sets in all different trials are mutually disjoint, which has some attractive properties in terms of independence. But as these folds will not be contiguous, by the way, in a real world scenario. It's just a schematic just to illustrate their disjoint, but they will not be contiguous, right? So this is one type of popular CV. Another popular CV is called repeated holdout, also shuffle split in some libraries. The idea here is to set aside a certain percentage for the coding and use the rest for training and tuning, right? So, for example, 30% in 30 for the reporting, and you repeat the process, right? You randomize, you split another 30% for reporting, rest for training and tuning, and you go on and on n times, typically like 50, 100, 500, depending on how large, how many parameters you're trying to compare and assess, etc. Right? So there is overlap in reporting sets, unlike k-fold CV. It's not a big deal, but this particular scheme is amenable to post-hoc statistics a bit better than k-fold CV. So there's many more variations, right, depending on which K you use. For example, two-fold CV means it's 50-50%, three-fold is 33% for reporting, etc. Reported holder also has many popular variations in terms of 50%, which is split half, 63%, like three-fold, etc. Right? So people choose different amounts depending on what they're trying to achieve, but you want to maximize the size of the test set when possible, right? So they could often stratify the training, tuning, and reporting sets depending on class imbalance. This really helps controlling the sensitivity of certain models, which can tend to be biased towards the majority classes, right? Like SVM, right? So to give you an example, very often we have a lot more healthy controls than MCI or other disease classes. So instead of just taking a fixed percentage from both, you take a fixed number of samples from the two groups for training, right? That way you could have different amounts of, that way training is not biased, right? So you could have the model trained on the same amount, but estimated on different size test sets or reporting sets or across classes, depending on it, right? We also have inverted very small training, but a large reporting sets, right? And leave one out could be leave one sample, leave one pair, leave one tuple, condition task, depending on your data set and goals, right? So many variations. So what do we choose, right? So what are the effects of different cross validation schemes? You might wonder, right? So that's the second question. So second goal I was trying to answer today. So here is how we try to measure the bias in cross validation measurements. Basically, given a data set, let's say this block we show here, we take a certain percentage for training and tuning. We run an inner cross validation loop. This gives us, assuming tuning as a reporting set, an estimate of performance. Let's call this cross validation accuracy, or inner cross validation accuracy, right? And based on a reporting set which we set aside, we can use the optimized model from this CV and estimate its performance on the reporting set. This provides us with one metric, reporting accuracy, right? If the particular cross validation scheme out of the many we just saw is structurally sound, and then you implemented it correctly, these two metrics would be more or less the same, numerical issues aside, right? If the structure is not sound, if there is some kind of bias, either due to class imbalance or the lack of independence or how we iterate extra, right? Let's say it could be positively biased, as in the cross-validation accuracy is much higher, but reporting accuracy would be low, or it could be negatively biased, whereas as in cross-validation accuracy is conservative or low, but the reporting accuracy seems high, right? But ideally, you want a scheme that's not biased, unbiased, without any bias, right? So let's compare different schemes so we can get some sense into it, right? So what we did, um, team from Parietal, is to use a large number of fMRI data sets as detailed here, and you can check into the paper, and run predictions with different cross-validation schemes, keeping tabs of cross-validation and reporting accuracies that um, that will allow us to compare biases across different schemes, right? So let's dive into the results we get from these data sets. So using a repeated holdout cross-validation scheme, like I mentioned before, we ran 10 trials, 20% for reporting, rest for training and tuning. This is the distribution of numbers. Just to walk you through this plot, what you see on the y-axis is the classifier accuracy from the inner cross-validation. On the x-axis is the accuracy in the reporting set, like I mentioned. And you can see that there is a large variance, okay, across the diagonal, right? What you want to ideally see is numbers following along this diagonal, which would mean this particular scheme is unbiased, right? But that's not what we see. What we see is a negatively biased scheme, and in some areas of the performance, and positively biased in some other areas, right? So, for example, in the high performances range, like 65% or above, you can see that it's negatively biased. Whereas in the low performance range below 65%, you can see it's positively biased, right? So keep that in mind, right? So just to give you a more concrete idea, so for when you implement the leave one sample out cross validation scheme on these data sets, this is the distribution of bias you get or across like all data sets, right? So we can see it's clearly positively biased. You know, the median is around even 20% actually to be, yeah. That's because you took only one sample out, they keep the n-1 for training and tuning, and it's known to be highly biased, right? Whereas when you make the reporting sets large enough, the bias actually comes down quite a bit, actually close to zero, slightly negatively biased, but close to zero, right? And when you take 20% for reporting with 3 splits, as in 3 repetitions, you can see it performing similarly. And as you increase the number, the variance goes down a little bit, but you can see it's mostly negatively biased, or although close to be unbiased. So in order to further understand their performance, because in the real data it's not really clear whether the numbers or biases is whether due to the schemes or due to some artifacts of the data. In order to get a good sense, we want to run some simulations with known ground truths and known suburbilities, for example. Right on the left, there is some overlap between two groups, whereas on the right they are fully separate, right? So we have some good grounded estimates of what we should expect in these two cases, right? So we also add time here to make them similar to the fMRI data sets here. So on these simulated data sets, when we read on the same experiments, for example, using leave one sample out, we can see that the leave one sample out still is highly positively biased, whereas leave one block out, it's completely unbiased. And with repeated holdout, same story, three splits. But as you increase the number of splits slash repetitions, the variance of the estimate really goes down. Like starting from 20%, three splits, it's about minus 10%, 11%, it goes down to 7%, right? So what it means is that this repeated holdout scheme with 20% left out is actually unbiased based on simulated data sets. So just to give you one more real world example of why it's a good choice, for example, there was a study in Europe's conference last year analyzing the Kaggle competitions on classification problems. Basically, they release a data set. There's public training data sets that you can take home and really train the heck out of it. And there is a leaderboard based on a public test set. As in, you can use that to actually tune your models and report them. There's a private test set which no one ever sees, especially the participants. Once you make your submissions are evaluated on the private test set to give you a little bit, right? But because it's a competition, people tend to try over optimize to public test sets. And the study tried to evaluate whether this reuse of the test set or reporting set in our case led to any overfitting, so to say, right? So basically comparing the performance on the public and private test sets, you can see whether the reuse actually led to any overfitting or not, right? So this is an example of different competitions, and you can see that the red line is mostly following along the diagonal line. There's some exceptions, of course, depending on dataset sizes and quirks of the dataset, but there are mostly the study shows that these reuse of public test set did not really show a drop in accuracy on the private test set. By test set, we mean the reporting set, right? So the key characteristics are that as long as the data set splits at IID, as in the difference between training, tuning, and reporting sets, their independence is maintained well, and when the test sets are actually large, as in at least 1,000 samples with 10,000 samples. Whenever the test sets are large and IID, test set reuse did not really cause any overfitting in these competitions, right? Which means that repeated holdout cross validation is a pretty safe choice. And I highly recommend that, which is actually also what I use in NeuroPredict tool I built to help newcomers and clinical people run predictive analysis. So another important aspect of cross-validation is how you handle confounds or covariates. They're often used interchangeably. So the important aspect is if you have confounds in your study, you must take care of them, as in regress them out or augment them or whatever you choose, while respecting the structure of the necessary. Remember that full setup I showed you, including the inner and outer cross-validation loops with training, tuning, and reporting sets. You want to make sure that the deconfounding is done within the training set and not anywhere else. not using data from anywhere else. It's very important, otherwise you're not handling it properly. And you also want to respect the data types of the confound. For example, some are often categorical, like gender, sex, site, for example, education sometimes, right? So you want to properly, instead of just giving some numbers, you have to take care of the data properly, right? Keep that in mind. I'll mention a library I'm building to help with this, by the way, later, but it's important to keep this in mind. So you split the data well, you take care of the training and tuning and deconfounding properly. But another important thing is to basically make sure the performance estimates the performance metrics you choose and estimate are actually commensurable across um, the cross-validation splits, right? So, for example, in this one repetition of cross-validation, you may get AUC 1, and as you repeat it, you can uh, get yeah, okay, where was it? Yeah. You can get different estimates of AUC, right? So AUC is actually commensurable across folds, but not all metrics are, right? For example, if you want to use decision scores from SVM, they are not, because the reference plane and the zero are changing, right? So you don't want to use decision scores across all folds to construct an ROC, because that would be invalid. That would just a garbage code, really, right? So you have to make ROC per fold and then average the ROC curves across the folds to compute that, right? So keep that in mind, right? So for example, in different splits, you have different SVMs because the plane is changing. That's what I need to say, right? Just to give you some concrete examples, if you take accuracy, it's actually commensurable across folds. It's a percentage fraction, and advantages is that it's universally applicable multi-class, but actually quite sensitive to class cost imbalance in the class imbalance in the data set, cost imbalance in the model or tuning, for example. You see the disadvantage is that it cannot be easily extended to multi-class problems, right? And similar other examples you can actually check out. Pausing here. I'm gonna skip through to get the talk done in time. So there's many other subtle sources of bias. What I presented so far and the data, those are measurable, experiment-wise programmatic bias, so to say. Here there's this what people call the expert bias, that are not captured in the data and features and tables, right? So one example is that people may try different Ks in K for CV and only report the one they like as in that gets their papers published. Or you may be trying different metrics and see where your model looks good to report that. So there is many such expert subtle bias or cheating, so to say. So keep that in mind. The best thing to do is always document and report whatever you did. Like it really doesn't matter, right? So avoid too much hacking. Then yeah, because results will not hold up with like excessive hacking when, especially when you try to replicate or somebody else tries to replicate, right? This is just to give you some examples. And also to give you a more intuitive feel for overfitting. For example, let's say these are the two groups. If you fit a model like this, for example, like an SVM, we'll refer to this as an underfit because you can see that there is some misclassification on both sides. Whereas if you try to fit something like this, in order to try to really separate the both groups as much as possible, you may call it overfit because it's not really a smooth or a simple model, so to say. Right? What we should be aiming for is something like this, so it's a good fit, maximizing the performance as well as the complexity, so to say. Right? We definitely don't want to avoid the overfit or underfit categories here. Just to give you a real world example of overfitting is this Google flu trend estimate. So take a look on the information here. There's also many other clever forms of overfitting besides the one I talked about before a few slides ago. Yeah, fun read. Take a look. So before I close, just want to give you a sense of the challenges involved with cross-validation or limitations, so to say. One of the main ones is that number of repetitions increases with sample size, right? If you have a larger sample, you want to repeat the cross-validation loop more times in order to actually get stable estimates to expose the model to variations in the data set, right? So this can be a problem with the model training is really slow or computationally expensive. For example, like all of deep learning, right? It's really slow. It requires a lot of resources. Or when the evaluation is actually expensive too, right? So you have to keep that in mind, balance it with your goals. And also when you have a huge model, and if you want to optimize over all parameters, that's something like a big problem because you have to run just as many number of cross-validation loops, it goes exponentially, right? It's a big problem. So based on all of this, here is what I recommend when you go on pursuing and implementing cross-validation in your analysis and research, right? So the most important point is you must ensure the training, the tuning and reporting sets are truly independent of the training set. As in, training must be independent from tuning, tuning must be independent from both the reporting and training, etc. You get the idea. You don't want to leak between splits. What's the point of splitting if you're leaking, right? Although some people are aware of this, it's actually very easy to commit mistakes when the analyses get complicated, especially when you have multiple dimensions of splitting in terms of subjects, sessions, or runs, trials, etc. Often terminology can get confusing and programmatic mistakes can be made. But so, which is why testing those implementation is very important, right? It's a safe choice, like I mentioned, to use repeated holdout CV, somewhere from 10 to 50% for tuning and reporting sets. Make sure you respect the sample structure, right? You want to keep the whole session together in the training or test sets. For example, a fMRI session because it's all the same thing. You don't want to split it into half, although there are many trials involved sometimes, right? So maximize the independence and handle confounds properly in the master CV, right? Without double dipping. Same applies, right? 3, choose your performance metric carefully. Like we showed you before, you need to know your goals, you need to know the limitations of a particular metric, and you want to actually not just use the right metric, but also pool it properly across different folds, right? So don't just consolidate decision scores from SVM across all folds. That's just wrong and garbage. Okay? 5th is try use the largest amount, largest reporting sets and largest number of repetitions, right? Because it really improves the stability and stability of the metrics you estimate, right? So conclusions are cross-validation is necessary to estimate our sample predicted performance, and we know why we need to do that. The results could vary, distributions bias could vary considerably with a different cross-validation scheme, and they can have a huge variance sometimes over 10%. Most importantly, once you do the right thing, you must also try report and document all the scheme in detail in terms of how you split it, how many times you repeated it, what's the full distribution of estimates across all the repetitions, etc. Right? For example, and also proper. For example, the good example for documentation is that you don't want to say, "Hey, I got 73% mean accuracy." With some standard deviation. There's no use, right? You want to fully tell the readers that, for example, you chose a repeated holdout CV with 80% reserved for training and tuning, You chose AUC as your metric, repeated it 100 times. Here is the full distribution of these 100 numbers coming from 100 different splits of your class validation, right? Then this will really help us. For example, you want to do post-hoc statistics to compare the two models, as well as the reader to judge what's really going on instead of just trying to imagine based on the medians, right? So most importantly, like I mentioned, proper splitting is not enough. It's important, essential, but it's not enough. You have to pool performance metrics properly across all folds, right? So keep these last two slides in mind. So there's more details if you want to dig in more. And libraries I mentioned. So to handle confounds properly, scikit-learn has some fundamental limitations in terms of passing along covariates or confound variables. So I've just released a major upgrade to NeuroPredict that enables you to do that based on this new library called confounds. So I really want to invite you to help me to increase their functionality further to ensure that your needs and applications are covered. I'll be working on this during the OHBM hackathon, as well as presenting a talk on this library at the Open Science Room. More details for these two tools can be found here, NeuroPredict and Confound. Follow me on Twitter, and I want to acknowledge the support from these institutions. So check my website for more details into various other software and research I do. And I would like to thank you for listening and paying attention. There's some jokes that you can pause on your video. So time to cross-validate and do it properly. You can always reach out to me if you have questions.
Hello, everyone. The title of my talk today is Confounding Variables, How Do We Account for Them? So here is the outline of the talk. So I'll start with a brief introduction to neuroimage-based predictive models. After that, I will discuss what are confounds in neuroimage-based predictive models. I will present and discuss some strategies to account for confounds, and then show some comparative results. And finally, I will give a machine learning perspective on the topic. So let's start with a brief overview of neuroimage-based predictive models. So here, I really just give a very brief overview. Since this topic, there is another lecture in the course that will give a more detailed introduction to the topic. So the goal in neuroimage-based predictive models is to train a predictive function with a set of training images and labels or targets, such that once we learn the predictive function, we can apply it to new test images to predict the labels. So here we can see the general pipeline. The first step of this pipeline is to use some feature extraction approach to extract features from the images. These features are then combined to create feature vectors, one for each sample or subject. We then have the feature vectors and the labels. This constitutes our data, which needs then to be split into training and test data. So we use the training data to train the model. So the output of the training is a predictive function, which can then be applied to the test data to make predictions. And we can use metrics such as accuracy for classification models and mean squared error for regression models. So we measure the performance of the models on the test data. Another output from the training is that if we use linear models, we can visualize the model weights. So we can see the relative contribution of the different image features to the predictive function. So one important question when using this pipeline is, how do we split the data into training and test? So actually, this depends on the sample size, and I will discuss that in the next slide. So I also give here just a very brief overview of how we split the data into training and test, because there's another talk in the course covering validation and cross-validation more deeply. So basically, if we are lucky to have a sample size that is large enough with hundreds to thousands of subjects, then or samples, then we can use a procedure called half split, that we split the data into two partitions, one for training, one for test, 50% for training and 50% for test. However, very often, that's not the case in neuroimaging studies, and we have to use some sort of cross-validation strategy. As, for example, the K-fold cross-validation strategy that I will illustrate here for a k equals to 3. So the way this procedure works is that we need to partition the data into different partitions. So here for a k equals to 3, we partition into 3 partitions. So we divide the data into 3 partitions. And in each fold, we use one of the partitions for tests and the remaining partitions for training. So here, fold 1, we use the first partition for test. Fold 2, we use the second. Fold 3, we use the third partition for test, and so on. So we then average the results across, the model performance across the different folds to give us an overall model performance. As I said, I'm overviewing this concept because I will be coming back to them when discussing the different strategies to account for confound. So now let's move on to the focus of the talk, which is confounds. And the first question we need to address is, what are confounds in neuroimaging-based predictive models? And although the concept of confounds is well defined in statistics, there is no consensus on what constitutes a confound in neuroimage-based predictive models. And different definitions have been used in different papers, and I will just show here a couple of examples. So a very common definition that is used in some paper is that confound is a variable that affects the neuroimage data and/or the targets, but is not of interest from a neuroscience or clinical perspective. Another definition from a different paper that's more narrow is that confound is a variable that is not of primary interest, correlates with the to-be-decoded variable, and is encoded in the neuroimage data. And the third definition from another paper is that confound is a variable that affects the image data and has an association with the target variable in the sample that differs from that in the population of interest. And here, an important concept is the concept of population of interest. So, which is the population that you'd like to apply our model, in which we'd like to apply our model. So in this case, in this definition, a variable is a confound only if its relationship with the target is present on the training sample, but not in the population of interest. And I will be coming back to this concept later in the talk. Now, as we could see, there are different definitions of confounds, so I will give some practical examples to make the definition a bit more concrete. So I will show some examples of variables that have been considered confound in neuroimage-based predictive models. So one example is predicting age from structural MRI data, considering sight or scanner as confound. Another example is predicting cognitive decline in demented patient from a structural MRI, considering age and sex as confounds. And a different example is predicting object category from fMRI activity patterns, considering luminance and spatial frequency as confounds. So in order to decide if we consider a variable to be a confound or not, we need to understand the reasons to account for confounds. So there are basically two reasons why researchers try to account for confound. One is to improve the generalizability of the models. For example, one might want to account for scanner-related noise in the images to improve the performance of the model in a multi-site study. Or one might want to account for confounds to improve the interpretability of the models. An example would be accounting for total brain volume in order to identify predictive brain features that are not influenced by overall brain size. So now I will just introduce some common strategies to account for confounds in neuroimage-based predictive models. So I will be presenting and discussing 4 different strategies. The first one is matching or counterbalancing. The second one is image adjustment by confounds, also known as regressing out the confounds. A third one is incorporating confounds as predictors, and the fourth one is instance-based weighting. And I'd like just to highlight that the first 2 are the most commonly used in the field and of neuroimage-based predictive models, although there are also some examples of the last 2. So before going introducing each of the different strategies and discussing them, I would like to introduce some notation that I will be using during the talk. So I will be using capital X in bold to represent the feature matrix. So it's a matrix that has the image features, and the features for each subject are included as different rows in this matrix, and these features could be, for example, the signal in the voxels of the image. I will be also using y, small y, bold, to represent a vector with the labels. Again, in each row I will have the label for a different subject or example, and the labels could be a clinical score that we want to predict, or age, depending on the predictive problem. I will also be using capital C bold to represent a matrix with confounds. Again, each row will represent the confounds for a different subject or example, and these confounds could be age, sex, scanner, and I will also be sometimes referring to a specific subject I. In this case, I will be using xi to represent the feature vector of the subject, so the set of features of a specific subject I, and I will be using yi to represent the label or target for xi, and ci to represent a vector of confounds for xi. I will also be using xj to represent a vector for features j across the different subjects. So now let's move on to the different strategies to account for confounds. So the first one is matching or counterbalancing. So here, the sample in this strategy, the sample is chosen such that there is no significant correlations between the confound variables and the targets. And matching can be done either a priori in the experimental design before acquiring the data, or a post hoc by selecting a subset of previously acquired sample. So an example of this procedure is matching patients and controls by age and sex in the training and the test data. The disadvantages of using this approach is that if we use this approach a priori, then the matched sample might not be representative of the population of interest. So we might have a training sample, and we try to design an experiment to acquire a training sample that will be matched by many different variables. However, it might be that there is an association between the target and the confound in the population of interest. So the matched sample might not be representative of the population of interest. So if we use this procedure post hoc, it can significantly reduce the sample size, because we have to use only the subjects that are matched. So an important consideration is that matching should be done across the different classes in a classification problem, and also across folds during cross-validation. I'll just show a visual illustration of how we could use this approach. For example, if a scanner is considered a confound in a specific predictive problem, then we have to make sure that the distribution of confounds is the same for the different folds, and also the same between the train and the test data. I'll now move on to the second approach, which is image adjustment, also called regressing out confounds. And here the goal is to remove the variability in the data due to the confounds. So to do that, we fit a linear regression model to each image feature using the confounds as predictors. The residues of the linear regression models are then used as input to the predictive models. An example of this procedure is regressing out age and sex from structural MRI and use the adjusted images as input to a predictive model. The disadvantages of using this procedure is that first, it assumes a linear relationship between the confound and the image features. And if this is not true, using this approach could potentially even add an additional confound to the image features. Also, if the confound variable is correlated with the targets, both in the training sample and in the population of interest, using these procedures might remove the predictive information from the image features, and we might end up with a predictive model that just performs at chance level. So in order to adjust all image features simultaneously, we can use some matrix equations to first estimate the model, the regression model parameters, and then the adjusted features. So here we would use these matrix equations to estimate the model parameters for all features simultaneously. And then once we estimate the model parameters, we can then remove the variability due to the confounds from the data in order to compute, to estimate the adjusted images. So I have already defined the matrix X and C hat here is the matrix C of confounds augmented with a column of ones to account for the bias in the regression. But this is just the simple solution, least square solution for regression. So one problem with this approach is that it is often applied before splitting the data into training and test, and this can lead to bias. So to address that, image adjustment should be done within the cross-validation framework, to avoid potential bias. In this case, the confound-image relationship is estimated based on the training data only. The way this is done is that we need to partition the X matrix, with the image features into a matrix with the training features and a matrix with the test features. And we also need to partition the confound matrix between training and test. And then the following matrix equations can be applied. First, we estimate the confound regression parameters from the training data, and then we can use these parameters to adjust the training and the test data. Again, C train hat and C test hat correspond to C train and C test augmented with a column of ones to account for the bias in the regression. So now I will show where in the general pipeline this approach should be included. So here, once we split the data into training and test, we can then use the training data to estimate the confound regression parameters, which can be applied to the training and to the test data to remove the effect of the confounds. So now I will move on to the third approach, which is incorporating confounds as predictors. So here, the confounds are included as predictors or as additional features in the model, and the goal is to explicitly learn the relative contribution of confounds to the predictive model. So an example of this procedure is adding age and sex as additional features to the feature vector containing the image features. The disadvantages of using this approach is that it's not easy to separate the contribution of individual features in the predictive model. So models' weights are usually difficult to interpret. Now, I will show how and where we can incorporate this procedure in the general pipeline. So here again, we have the images, we have the labels or targets, and now we have a set of confounds that we'd like to incorporate in the model. So we can add then as additional features to the feature vector. So now we have a set of features correspond to the confounds. And the difference is that once we compute the model's weights, we also have weights to the confound. So we have weights not only for the image features, but also for the confounds. But as I said before, if in particular, if we use non-sparse approach, it's really difficult to interpret and identifying the real contribution of individual features to the predictive model. So if we use a sparse approach that selects a subset of relevant features for the prediction, then we might get some insight about the contribution of the confounds to the predictive function. I will now move on to the fourth approach, which is instance-based weighting. So here, the goal is to weight the sample to produce a pseudo sample in which the association between the target and the confounds has been removed. So instance-based weighting proceeds in 2 stages. In the first stage, it models the relationship between the confound and the targets. And in the second stage, this relationship is used to weight the training samples in the predictive modeling. So the disadvantage of using this approach is that in case of high-dimensional data, it does not demonstrate a clear advantage over the other methods in terms of overall performance. So a bit more information on how this procedure works. So in order to perform instance weighting, we first need to estimate weights, WI, for each training example. This involves estimating the ratio between the marginal and the conditional distributions P of Y and P of Y given C from the training data and evaluating the weights at each training point I. And once we have the weights for each training point, then the next step is to learn a weighted predicted function. For example, we can learn a weighted Kanner-Ridge regression in which the loss associated with training point I is weighted by WI. So now I will show where in the general pipeline this approach can be included. Again, once we split the data into training and test, we can use the training data to estimate the weights for each training example or training point. And after that, we can learn a weighted predictive function. I will now move on to show some comparative results across the different approaches. And before doing that, I will introduce an experimental design that was proposed by Mourao, who was a postdoc in my group a couple of years ago and did a very deep work on confounds. So he proposed this experimental design to compare different approaches to account for confounds. So it starts, the procedure starts with a definition of a population of interest. So these are populations in which we would like to apply our model, our predictive model. So in this illustrative example, we would like to predict the clinical scores from brain images. And we have males and females in our sample. Males have, in average, larger brains than females, but there is no associations between the sex and the clinical score that we would like to predict, although there is an association between head size and the clinical score. So small people with small heads, smaller heads tend to have higher values of the scores, and people with bigger heads tend to have a lower values of the scores. We then create 2 samples from the population of interest. One is a bias sample in which there is an association between sex and the clinical scores. We can see here that males tend to have higher values of the scores and females tend to have lower values. And we also create an unbiased sample from the population of interest. So here there's no associations between sex and the clinical score. So this unbiased sample is representative of the population of interest. So according to the confound definition that Mourao gave on the paper, sex is a confound in the biased sample. So he then used this experimental design in 2 predictive problems, to compare the different strategies to account for confound. The first one was training a model for predicting mini-mental state examination from a structural MRI. So here, a biased and an unbiased sample were selected from the ADNI dataset, which is a public dataset that contains subjects with dementia, mild cognitive impairment, and healthy subjects. So in this case, the biased sample contained a correlation between sex and MMSE scores, and the unbiased sample did not contain a correlation between sex and MMSE score. So now we see here the results. So here we have the different models. You know, the first one is called here images only, is the baseline model where there is there was no approach to account for confound. Then we have the second model here, which is the adjusted images. It corresponds to regressing out the confounds from the data. Then we have the third model, which is images and confounds, is including the confound as predictors. And the third one is, or the fourth one is the instance weighting. So just to emphasize, we have the baseline model and three different approaches to account for confounds. So here we have two columns with results. The first one are results when we train the model using the biased sample, and the second is when we train the model using the unbiased sample. Let's first focus on the results for the biased sample. We have here the mean squared error. What I want to emphasize is that in both cases, the test sample was unbiased. So the model were tested using unbiased sample. So what we can see here when we compare results for the biased sample is that the results, all models perform better than the chance level. The mean squared error is relatively, it's very similar, actually. And what we can see is just that adjusted image or regressing out confounds gave slightly better performance, so the smaller errors, the smaller MSE. Now, when we look at the results for the unbiased sample, what we can see is that now the performance is quite similar across the different models, but of course the training sample was unbiased in this case. What we can also observe is that the results when training with unbiased data was always better than when training with biased sample. Even though we try to account for the bias or for the confound, it's always better to have unbiased training sample. So now I will show the weight. So here we can see the average weight map for each model, trained to predict MMSE scores from a structural MRI. And what we can observe is that there is not much difference across the different approaches, and neither across the different samples, the biased and the unbiased one. And now I'll move on to the second example, that was training a model for predicting age from a structural MRI. So here, a biased and unbiased sample were selected from the ICSI dataset, which is a public dataset that contains images from healthy individuals. In this case, the biased sample contained a correlation between age and site. This was a multi-site study. And the unbiased sample did not contain a correlation between age and site. Again, we have similar table with the results. We have the baseline model and three different approaches to account for confounds. So if we now focus first on the results for the biased training sample, we can see that all models perform above the chance level. The results were also relatively similar across the different approaches, and we can see here that in this case instance weight gave slightly better results, and the worst results were when using adjusted images or regressing out the confounds. Now when we look at the results for the unbiased training sample, what we can see is that again there's no much difference between the performance of the different models, but when we compare results between training with unbiased versus biased sample, results were always much better when using the unbiased training sample. Again, we can see the weight maps for the different models here, trained to predict age from a structural MRI now. And what we can see that similar to the previous example, there is almost no difference between the different approaches and even the different samples, the biased and unbiased. So now, to summarize these results, we can make a few observations. The first one is that all models perform better than chance. So they were able to learn useful predictive information from unbiased data to predict. So they were able to predict useful information to predict unbiased data, despite the fact that the training sample was biased. Another observation is that all models perform better when training with unbiased samples compared to when using biased sample. Another observation is that the performance of the different methods for dealing with confound varied for the different data sets. And one explanation for this is that different confounds might have a different effect on the data and might require a different approach to account for their effect. So another observation is that none of the methods gave more accurate predictions than the baseline images only model for both data sets. And finally, including confound as predictor gave less accurate predictions than the baseline model for both data sets. So now I want to make another important point which is we should also account for confound during significance testing. So if we are using a permutation test, then we should use a constrained permutation. For example, we should permute the targets within the site when considering sites as confound. This procedure preserves the associations between the targets and the confounds while breaking the relationship between the image data and the targets. And this procedure is important even when we use an approach to account for confounds. So now I will move to the last part of the talk, and I would like to give a machine learning perspective on the problem of confounds. So the problem of confound is related to the dataset shift problem in machine learning. And dataset shift occurs when the distribution of the training and the test set don't match. So examples of dataset shifts are covariate shift, when the distribution of the features in the training and test sets are different. Prior probability shift, when the distribution of the targets in the training and test sets are different. Sample selection bias, which is when the distributions differ as a result of a known sample rejection process. And different approaches have been proposed in the machine learning field for dealing with dataset shift. So I'm having a reference here of a book who gives a description of dataset shifts and different approaches that have been proposed in the literature for people who might be interested. So similar problems are also investigated in domain adaptation and transfer learning. So in domain adaptation, the aim is to learn a model from a source data distribution that performs well on a different but related target distribution. And one example of domain adaptation could be adapting a predictive function trained on data collected from one scanner to make it compatible with testing data obtained from a different scanner. So in transfer learning, the goal is to transfer knowledge gained while solving one problem to a different but related problem. So one example of transfer learning could be training a classifier to discriminate Alzheimer's patients from healthy controls and then fine-tune it to classify frontotemporal dementia patients from healthy controls. And one reason why one might use this approach is when we don't have a sample of frontotemporal dementia patients large enough to train the model. So we might want to pre-train the model with another, a different but and somehow similar group, and then fine-tune the model with the patient population of interest. So I want to finish here saying that I think there is a huge potential for techniques from domain adaptation and transfer learning to be applied to neuroimage-based predictive models to address some of the problems that we encounter with confounds. So now I just want to acknowledge my lab, who support all the work I do, and also acknowledge some previous members of the group that did a substantial work on confounds, and the Pronto team. Pronto is a pattern recognition toolbox for neuroimaging data analysis that we support in the group. And I also added some useful references to the slides. I hope they are useful, and some useful tools. So thank you very much.